Hey everyone, welcome back to our Unit 3 dynamic study. Here we're focusing on Newton's third law and non-perpendicular applied forces. Just a quick review of what we've been studying the past week or so. First, we're going to look at Newton's first law. An object at rest stays at rest. An object in motion under constant motion remains in motion unless acted on by an outside force. Once again, the more mass the object has, the more inertia it has. Newton's second law is stated as this. Net force equals mass times acceleration, which basically stated in a phrase is an unbalanced forces caused accelerations. So the famous equation F equals ma basically is an unbalanced force, a net force, causes a mass to accelerate. The last thing which is important is obviously what is a force. And a force is basically anything that is pushed or pulled, right? A push or pull is what a force is. Forces result from interactions. There can be a normal force, a frictional force, tension, applied forces, all different kinds of things. Those are what causes forces. And then according to Newton, we're working on our Newton's third law here. Two objects interact with each other. They must exert forces upon each other. So a quick example is when you sit down in your chair, your body exerts a downward force on the chair. The chair exerts an upward force on you. These two forces are called action and reaction forces. Sometimes we call them action-reaction pairs. And so on that note, here's Newton's third law stated. For every action, there is an equal and opposite reaction. The most important part about this is this equal and opposite thing, right? So we've heard about this for a really long time, but basically what it means is anytime two forces act on each other or two objects act on each other, there is an equal and opposite force on that. So a quick example about an action-reaction pair is a fish that uses its fins to push water backwards, right? So as it swims through the water, a push on the water will only serve to accelerate the water. Well, since forces result from mutual interactions, the water must also be pushing on the fish forwards. So to think of it simply, the fish push water, the water push fish. That's the easiest way to think about how a fish can swim through the water. Another way to think about this is using a sailboat, right? The wind push sail. Well, the sail must also push back on the wind. It's kind of an interesting way to think about it, but that's exactly how we do that. Another example that we talk about is a bug striking the windshield of a bus or a car and makes a big mess. This is a clear case of Newton's third law of motion. The bug hits the bus and the bus hits the bug. So one of the questions that will always be asked on these on these tests and quizzes is which of these two forces is greater, the force of the bug on the bus or the force of the bus on the bug? And once again, Newton says they were equal. They both experience the same amount of force on each other. The trick, what happens here, is the bug is accelerated at a far greater rate than what the bus is. So down here I have my example here with the physics elephant on their physics skateboards and Sir Isaac Newton, right? So what happens is they both are generating a net force on each other. What happens though is Sir Isaac Newton has such a small mass but is accelerated at a far greater rate than the elephant, who has a big mass but is accelerated at a smaller rate to the right here. So Isaac Newton, small mass, big acceleration. Elephant, big mass, small acceleration, all because the same net force is acting on them. If that net force value doesn't change, that means that I have to have these interactions between the mass and the acceleration. They have to be directly related to each other. Big acceleration must have small mass. and big mass must have small acceleration. That's kind of how we think about these things. All right, on to some of the example questions that you guys will see. Here's two boxes connected by a cord. There's the light cord. The light cord, once again, is a massless cord. The smooth table means there's no friction. And we're supposed to find the acceleration of each box and the tension in the cord connecting the two boxes. So the first thing we want to do is draw the free body diagram of each. And here we have our free body diagrams. We have the mass B, the 12 kilogram mass, with its force of gravity pointing downward, its normal force pointing upward, and the tension in the string pointing to the right. Notice there is a frictionless table here, so there is no friction represented in this diagram. Here we have box A. It has four forces acting on it: the force of gravitation down, the normal force pointing up, the tension pointing to the left, and then the force of the pull is pointing to the right. Notice how we have the two tensions pointing to each other. In a problem like this is an example of Newton's third law. We have an equal and opposite reaction in the tension that is connecting those two boxes. So the first question asks us to find the acceleration of each box. And that's an important idea right here. These two boxes, they're connected. They're creating a system. And what's telling me is the system is accelerated because they're connected. So both boxes must accelerate at the same rate. So once we draw our free body diagrams, we have to go down and start working on Newton's second law here. And what's happening here is the net force on box B is basically just the tension. Once again, we're assuming that net force in the y direction is 0. The object isn't accelerating off of the table. We know that the normal force of B is equal to FGB, and the normal force of A is equal to FGA. And one of the reasons we're not going to worry about this too much is, once again, friction force is mu times the normal force, but the problem stated we are not dealing with friction, so we're really not going to bother with it at this point. So back down to here, we have our net force equals the tension. The tension is creating that net force. And I know, because these objects are being accelerated to the right, this net force is causing some kind of acceleration to that mass. So we have this idea here. This tension is causing mass B to accelerate to the right. For the other one, the net force is created by the interaction of the pulling force pointing to the right minus the tension pointing to the left. And it is ma times a, the acceleration there. Once again, both of these accelerations are pointing to the right. In this case, we can have our two equations here. We have tension is equal to mb times a, and over here, fp minus t is equal to ma. Noticing we have tension in both, we can plug these guys in. Fp minus, I'm going to underline this real quick so I have mba equals mass of A times A. We identify which pieces are together here. And at this point, I went ahead and plugged everything in. Fp is 40. MB was 12 times A. Mass of A is 10 times A. And then it becomes a pretty straightforward algebra piece here. 40.0 equals 22A. And when I run the math, I get 1.8 meters per second squared to the right. So that's part A. So it looks like a lot of steps here, but once again, drawing these free body diagrams is pretty critical to making sure we understand which way the forces are acting. The other piece that asked me, part B, is what is the tension in the cord connecting the two boxes? So basically we're looking for T, what is the tension? Back down over here, I have this tension equals MBA. Once again, this was the only force in the horizontal direction acting on block B. So tension equals mass of B times A. I already figured out what the acceleration was, so I go basically back in and back substitute the values here, which is 12 for the mass. My acceleration was 1.8. So the tension in the string was 21.6 newtons. And once again, tension is kind of just this weird transmission of force that's going on between these two guys right here. So you really phrase it like this. The tension in the connecting cord is 21.6 newtons. You don't really make it have a direction or anything like that until you start plugging it into the rest of the mathy stuff that you have to do. All right, so that's the first kind of question you have. A box connected, two boxes connected by a cord in the horizontal direction. In this question, we have no actual numbers, but we're going to solve it symbolically. I know all of our favorites. And I'm going to try to solve it in such a way that we break it down to everything, to its base components, so that we understand where all the pieces are. So very quickly here, we have these two masses connected by the strings. So this is very similar to the questions we were talking about, our quote-unquote elevator questions, where if an object is either pulled up, let down slowly, or held at the tensions do something kind of funny. Well, in this case, the same thing kind of happens, although there's now more than one mass attached to it. In this question, we're assuming that the objects are accelerated upwards. So like the previous question, they're connected by the string, therefore they're a system, which means they both must accelerate at the same rate. Once again, we're going to draw the free body diagrams for these. This is mass 1. Mass 1 has the force being pulled up on it. And mass 1 has two forces acting in the downward direction. It has the tension in the string connecting the two things, and it has the force of gravity, Fg1, pointing down on it also. Once again, remembering that the acceleration is pointing upwards. For M2, his free body diagram is a bit simpler. There's just a force of gravity pointing down, call it Fg2, and then tension pointing up, knowing that once again there's acceleration pointing in the y direction. Again, understanding Newton's third law, these two guys are the same force, they're just pointing in opposite directions. That's usually the key to solving these, is understanding what's going on there and setting them equal to each other at some point based on what we know. So net force for the first object is M1 times A. It's moving up in the positive direction. And once again, the net force is the interaction of the force pointing up, Fg1 pointing down, and tension pointing down. So when I plug those in, I get F minus Fg1 minus tension equals M1A. So once again, we just are substituting things in. And then I'm going to break this down one more time. Oh, sorry, that should be a minus, not an equals. Minus M1G minus tension equals M1A. Broken down like this, we can kind of see what all of the components are doing. Once again, this is a positive acceleration in the upward direction. We do the same thing to the second block. The net force on the second object is M2 times positive A. if you'll notice, his free body diagram looks identical to our quote unquote elevator questions that we worked on the other day. Net force for 2 is tension minus Fg2. Substituting everything in, T minus Fg2 equals M2A. So tension minus M2G equals M2A. So once again, we have this acceleration. It's pointing upwards. We have the same variable t in both of those, and that's going to be the way to solve most of these questions. You'll just identify which one is t. Here you can see t is m2a plus m2g. We kind of talked about that last time. We would get that whole value and plug that in based on what I knew about the question. So just understand these kinds of questions. There's so many different variables or so many different kinds of questions we can ask. So I decided to kind of give you the nuts and bolts version. That way we can go whichever direction we need to go with it. All right, on to the next one. Here on these we have adding force vectors, and so we already got pretty good at this. But here, basically, we're calculating the sum of the two forces exerted on the boat by workers A and B in the figure. So we have two forces. We have FA pointing over here at 40 newtons at 45 degrees. And so we have to think back a little bit, but there is a FA in the X direction and an FA in the Y direction. And remember, this is FA cosine theta. This one is FA sine theta. So when I plug in the math, I get 40 sine 45. This is 28.3 newtons in the Y direction. And yay, good thing it's a 45-degree angle. That means it's 28.3 newtons in the X direction. FB is here down at 30 newtons. This is FB here. This was FA, forgot that guy. And once again, here's my angle. In this case, it is 37 degrees. So I have an X direction, we'll call that FBX. And that is FB cosine theta. And then I have FB in the Y direction, which is FB sine theta. Plug everything in, I get 18.1 newtons for the Y direction going down. And for the X direction, I get about 24 newtons to the right. So first thing we do is add everything up in the X direction. Net force in the X direction is FA in the X plus FB in the X. So 28.3 newtons plus 24 newtons. So I get a net force in the X direction of 52.3 newtons. In the Y direction, it's FAY pointing up minus FBY pointing down. So I get 28.3 pointing up, and pointing down is 18.1 newtons. So net force in the Y direction is 10.1 newtons. Going back to our old school way of plugging all these things in, I get the net force in the X direction of 52.3 newtons. In the Y direction, I get 10.1 newtons. To find the magnitude of F is the Pythagorean theorem. So 52.3 squared plus 10.1 squared, take the square root. So the magnitude of F is 53.3 newtons. We also need to figure out what the angle is. So the angle is the inverse tangent of the y chunk over the x chunk. So your angle is about 11 degrees, and I'll call it to the x axis, simply because that's kind of how they gave me my information up there. Okay, so pretty quick one. Once again, a lot of work, but it's nice to see where all of that stuff comes from. All right, on to the last question, or the last kind of question you will see. So on this question, we have basically a box being pulled along with some coefficient of friction. So nothing we haven't seen before. The one thing we are adding to the question is something about the angle that the box is being pulled at. So here's a sketch of what the question looks like. We have our box over here with the forces acting on it. Once again, I always know that FG is pointing down. He's always there. I have a normal force. It's pointing up. I have a friction force pointing to the left, for example, here. And then I have my applied force. I'll call that F sub P at a 30-degree angle above the horizontal. So I want us to kind of make sure we make a note about the normal force here in a little bit, and make sure we talk about that. But here is the diagram that we're assuming is going on. One of the things we have to be sure about is we're assuming still the net force in the y direction is 0 newtons, and this is kind of where we'll start here. Everything going up minus everything going down is equal to 0, but now we have this force acting at an angle, which means there is an FP in the x direction pointing this way, and an FP in the y direction pointing up. I have to use these angles, or I have to use the components in order to solve what's going on. So in the net force in the y direction, the forces responsible for that are the Fn, the Fpy in the up direction, and Fg in the down direction. And subbing these two things in, they're equal to 0. And a quick note on the normal force. You know, previously we've said the normal force is equal to Fg for everything, and that's true for a majority of the time. Well, in this case, take a look at what the normal force happens to it here. When I solve for the normal force, it is no longer equal to Fg. It's actually a little bit less than Fg, because I'm pulling up on the angle, which I'm basically taking some of the weight off of it. And it seems to make sense. If I'm dragging something heavy across the floor, I would rather pull it up at an angle versus down, because as you can imagine, it would increase the normal force. And so we'll do a quick example about what that looks like at the end of this guy. But here's what the normal force is. Now the question basically assumed there's an acceleration in the x direction. So we'll have my f of x equals mass times acceleration. Well, the things responsible for causing the acceleration in the x direction are going to be the x component of that pulling force, and then the friction force is opposing it. Subbing those two guys in, I'll have Fpx minus the force of friction is equal to mass times acceleration. And on these, I like to take these down as far as I can go, simply because it makes sense to where they are coming from. Fpx, that's going to be Fp cosine 30. That's the x component of that guy. Friction force is defined as mu times the normal force equals ma. Now we just finished working on the normal force. Normal force over here is actually Fg minus Fpy. That Fpy, I'm gonna write it up here real quick, is just Fp sine theta, or in this case sine 30. So I'm gonna go ahead and write all that in. Fp cosine 30 minus mu times the normal force, which is Fg minus FPY equals MA. And once again, all I'm doing is breaking everything down to its base components. Here's the rest of that solved, or at least broken down. Solving for M, or solving for A, means divide by M. So I get a big long equation that looks something like this. Divided by mass. And if we did everything right, hopefully we get something like 1.12 meters per second squared to the right. So sorry, 1.12. So once again, there's lots of math that you have to do, making sure everything goes and stays straight in that order. One of the things to be careful of is understanding what's happening with the normal force. It is being pulled at an upwards angle, which means the normal force is no longer equal to Fg. It's actually a little less than Fg. It's less by the y component of whatever that pulling force is. All right, lots of information here, lots of diagrams, lots of stuff to draw, lots of algebra to do. Make sure we keep everything straight. We have some example problems to do, or problem set. Once again, we're not really going to be worried about turning those in right now, but I do want you to go through those, and we will go through the answers on those when I get back. Let me know if you have any questions. Thanks for watching. Bye.